Hello, my name is Hagir from Chalmers University of Technology, and in this presentation I'm going to talk about our joint work with Mustafa Hagir from Tehran Polytechnic on hierarchical correlation clustering and tree-preserving embedding. In this work, we first extend the well-known correlation clustering to produce hierarchical clusters at different levels, which we call it HCC. Then we study unsupervised representation learning and feature extraction from HCC. And finally, we study the extension of minimax distances to be used with correlation clustering. We are given a dataset with n objects where the matrix S shows the pairwise similarities between the objects. The elements of S can be positive or negative. We may convert the pairwise similarities to dissimilarities simply by negation. Then a hierarchical clustering solution is shown by T, which is an ordered tree. The function dis, defined between U and V, denotes the intercluster dissimilarity between these two clusters. Linkage of V returns the dissimilarity between the children of V based on the dis function which is used. And level of V is defined as the max of level of P and level of Q plus 1, where P and Q are the two child clusters of V. Starting with standard correlation clustering, which generates K-flat clusters, the respective cost function can be written as following, which essentially accounts for the sum of the pairwise dissimilarities between different clusters. Then, motivated by this, we can consider the following linkage function to be used by our HCC model. The linkage function in this way is defined as sum of the pairwise dissimilarities between the objects in two different clusters. Then, using this, we can follow an agglomerative method in order to produce clusters at different levels. We start with each object being in its own cluster, and then at each step we merge the two clusters which have a minimal distance, and the distance is defined according to this function, until at the end we have only one cluster at the highest level. It is possible to see that any hierarchical clustering solution, including our HCC model, can induce a sort of distance function between the objects according to the way the objects join to form the hierarchy. One such an option is defined here in this equation, where xij, the hierarchy-based distance between I and j, is defined as the level of the cluster at the lowest level, which contains both I and j. Then with this distance function, we will have a matrix corresponding to the pairwise distances between the objects. We can then use the ultrametric property of X and apply an embedding method like multidimensional scaling in order to extract a set of relevant features. And in this way, we can use this hierarchy, like HCC, for the purpose of extracting a set of features in addition to performing hierarchical clustering. We finally study the combination of correlation clustering with min-max dissimilarities. Given graph G, whose nodes are the objects or items, and the H weights are the pairwise dissimilarities, then the min-max dissimilarity between I and J is defined as following. Over this graph, we consider all the paths between I and J, and for each specific path, we choose the edge with maximal weight. Then, among these maximal edge weights, we choose the minimum of them. So, in this way, min-max dissimilarities are shown to be effective in extracting elongated patterns and complex structures from data. Then, according to Theorem 1, we show that min-max distances when combined with correlation clustering not only help to achieve this, but also can reduce the computational complexity from NP hardness to polynomial time. In the following, we demonstrate the performance of HCC compared to the alternatives on a number of UCI datasets. In this plot, the x-axis shows the noise level, and the y-axis is the evaluation metric, which is the adjusted mutual information in this case. According to the results, we observe that HCC yields significantly better results and also is more robust. And finally, we study the application of HCC for feature extraction. In these experiments, we apply different agglomerative clustering methods, either for producing the final clusters or for extracting a set of features, where then we apply GMM to produce the final clusters. According to the results, we observe that HCC is always effective, either for producing the final clusters or for extracting a set of relevant features. And in particular, we see that the combination of HCC and GMM can be even more effective. With this, I conclude the presentation. You can find more details in the paper, and if you have questions, please feel free to contact me.